We've all stirred a cup of coffee. It seems like the simplest thing in the world, right? But what if that cup was a 10,000-gallon tank, and instead of coffee, it was something like life-saving medicine or the paint for a brand new skyscraper? Well, that's when stirring stops being simple and becomes this incredible, complex field of engineering.
I mean, think about it. You pop open a can of paint, and it's just one single, consistent color. Or you take a pill and you just trust that the right amount of the active ingredient is perfectly mixed in. None of that happens by accident. It's all thanks to the hidden science of mixing.
And here's the classic definition that engineers have been using for decades. The key phrase here is a desired level of uniformity. The whole game is about taking different materials, liquids, solids, whatever, and blending them so thoroughly that the final product is exactly the same everywhere.
So how do you actually do this on a massive scale? I mean, you can't just stick a giant spoon in there. You need highly specialized tools, and in the industry, they're called agitators. Let's take a look at the actual hardware that makes all this happen.
Okay, so generally, agitators fall into two big families. On one side, you've got your high-speed guys. They have smaller blades, and they're perfect for thin liquids, things like water or juice. But for the really thick, gooey stuff, think toothpaste or heavy glue, you gotta bring in the big guns, the low-speed agitators with these huge, sweeping blades. And just look at the variety here. This is what's so cool. You've got everything from what looks like a simple boat propeller to these crazy complex helical ribbons that look like giant corkscrews. Each and every one of these is a custom solution engineered for a very, very specific mixing problem.
But the shape of the blade is only half the battle. The real secret, the magic, is in how it makes the liquid move. It's not just about spinning it around in a circle. It's about creating and controlling very specific patterns of flow.
So let's look at two of the most common high-speed tools to see what I mean. On the left, you've got the workhorse of the industry, the flat blade turbine. And on the right, something we all recognize, a marine-style propeller. They both spin fast, but oh man, they get completely different results.
The turbine is all about what we call radial flow. It literally slings the liquid outwards from the center. Imagine you're on a fast-spinning carousel. That force pushing you out, that's exactly what the turbine does to the liquid. It smacks it against the tank walls, and from there, it circulates up and down.
The propeller, on the other hand, creates an axial flow. Think of it like a really powerful ceiling fan. It pushes a strong column of liquid straight down to the bottom of the tank. Once that column hits the floor, it spreads out and flows back up the sides. So you get this amazing top-to-bottom circulation throughout the whole tank.
Okay, so here's a classic problem every engineer faces. If you just stick one of these agitators in a smooth round tank and let it rip, you get a vortex. You know, that big whirlpool you see when water goes down the drain? Well, in industrial mixing, a vortex is your enemy. It's super inefficient, it can suck air into your product, and it can even damage the equipment. The solution? Surprisingly simple. You install these vertical plates called baffles along the tank wall. They completely break up that swirling motion and turn it into really powerful, effective top-to-bottom mixing.
All right, so you've picked the right agitator and you know how to kill the vortex. How do you put all the pieces together? Well, this is where we get into the actual blueprint, the precise geometry that goes into designing a perfect mixing system. Now, this might just look like a simple drawing, but for an engineer, this is the gold standard. It's called the standard tank configuration, and it lays out the ideal relationship between the size of the tank, the amount of liquid, and the placement of the agitator.
And the secret is right here in these ratios. For example, the agitator's diameter should be about 1/3 of the tank's diameter, and its height off the bottom, also 1/3 of the tank's diameter. Even the width of those baffles we talked about is super specific, 1/10 of the tank's diameter. These aren't just random guesses. They're proportions that have been tested and optimized over years to guarantee the most efficient mix possible.
So we've got the design locked in, the geometry is perfect, but now comes the next big question every engineer has to answer. How much horsepower do we need? How much energy does it take to actually run this thing?
Now, don't worry, we're not going to do a math quiz. All this equation really tells us is something that kind of makes sense intuitively. The power you need goes up if the liquid is thicker, if you spin the agitator faster, or if the agitator itself is bigger. More liquid, more speed, more size, it all means you're going to need a bigger motor.
This power curve is such a cool way to visualize it. It basically tells a story. On the far left, you're in the thick, slow, viscous range, and things take a lot of effort. As you speed up and move to the right, you go through a transition. But then you hit this sweet spot, the fully turbulent range. And here, something really interesting happens. The power you need starts to level off. You can get more mixing without a huge energy penalty.
So, you've designed the perfect system, you've figured out the power requirements, and you've got your recipe perfected in a little lab beaker. Now comes the biggest, scariest challenge of all, making it work in the real world.
This right here is the million-dollar question in chemical engineering. It's a process called scale-up, and it is notoriously hard. Something that works beautifully in a small glass beaker can go completely, disastrously wrong in a giant steel tank if you don't scale it up correctly.
So how do they pull it off? Well, first, they have to maintain that geometric similarity we talked about. The big tank has to be a perfect scaled-up replica of the small one. Then, they pick a key performance metric to keep the same. For some processes, that means ensuring the tip of the agitator blade is moving at the same speed in both the beaker and the giant vat. For others, it's about making sure every single liter of liquid gets the exact same amount of power pumped into it.
So the next time you use a product that's just perfectly consistent, perfectly uniform, remember what it took to get there. From the exact shape of the blades to the precise geometry of the tank, all the way to that incredible challenge of scale-up. That perfect mix is never, ever an accident. It's pure, brilliant engineering, a hidden science that's literally all around us.